Greetings, fellow nerds. I'm going to dissolve this bar of platinum to make this expensive chloroplatinic acid reagent. And I'm going to try and do it to some professional grade standards rather than my usual basement amateur grade. A friend of mine needs chloroplatinic acid for their work, and rather than order it from Sigma Aldrich or waste their valuable time to make it, they've asked me to waste mine instead, and I readily agreed. First, the preamble. I've previously dissolved an ounce of platinum to make chloroplatinic acid, and you can watch those videos linked in the video description. That was way back in 2012. Just so you know, there is nothing new in this video that wasn't covered in the old videos. But I've decided to film anyway since I'm told there is something relaxing about watching someone who's passionate about their work. So if you're still watching, let's get started. First, I gotta clean up my lab. Yes, I know full well my workspace looks like a Colombian drug lab at times, but in my defense, you shuddered how dirty actual professional labs can sometimes get. And there we are. Now my glassware has been washed and cleaned already, but after years of use in my amateur videos, there might be some residues caked in. So I'm going to need a much more thorough cleaning process. First, I bake it in a furnace to 500 Celsius. This is rather extreme, but at 500 Celsius, pretty much all organic compounds and residues are burned away. A lot of inorganic compounds are oxidized, and many salts will just straight up evaporate. Baking, or pyrolyzing as it's called, is a great way of deep cleaning glassware. But not all glassware can take it. Borosilicate can handle 500 Celsius because this is well below the softening point at around 800 Celsius and a bit below the annealing temperature of 600. But other glasses can warp, soften, or even shatter at these temperatures. You could use lower temperatures for other glass types, but too low and some organics like carbon residues can survive. So be careful and only pyrolyze borosilicate. I left it in the oven overnight. And here we are the next day. The beaker is cooled and every trace of organic and volatile compounds have burned away. I did the same treatment to this flask since I'll be needing both. Now we have to clean out the non-volatile compounds that survive that temperature. To do that, I add 50 milliliters of water, 50 milliliters of hydrochloric acid, and 4 milliliters of nitric acid. Then I heat it on the hot plate and put the flask on top with water to form a reflux setup. What I'm doing is creating a weak version of aqua regia that will oxidize and dissolve most non-volatile inorganic compounds. This should clean out any remaining residues. I'm also doing this so I can experiment with the temperature settings and see what settings will boil or simmer the aqua regia. I want to know this so I have an idea what settings to use for the platinum and aqua regia reaction later on. I'm going through all this cleaning trouble because I want to minimize contaminants for the work my friend will be doing once they receive my product. I would expect them to do no less for me if our roles were reversed. And before you ask, yes, they've reviewed my procedure and deemed it acceptable for their work. Fortunately, they don't need semiconductor-grade chloroplatinic acid, which is beyond my ability to provide. So I left the aqua regia refluxing overnight to ensure a deep clean. And there we go. I turned off the heating and let it cool. Now we just clean out the glassware with deionized water and let it dry. While that's going, I need to calibrate the lab scale. Every scale has its own procedure, and for mine, I just need to calibrate it against one standard calibration weight of 200 grams. More expensive scales use multi-point calibration with multiple calibration weights, but my friend doesn't need that kind of precision. Now that's calibrated, I'm testing it by putting the same calibration weight back on. This scale has a manufacturer-specified error of about 3 milligrams, so as long as we're within that, it's accurate and consistent. And it seems to be good. So now we weigh the platinum bar to verify and record the mass. I'm doing this so I can accurately divide the chloroplatinic acid later. I'm weighing a few times to ensure the readings are consistent. Technically, I should be using a plastic weighboat or weighing paper. The scratching of the bar against the metal weighing dish theoretically contaminates the platinum with trace metal from the dish, and vice versa. But I'm not going to bother. This is not meant for semiconductor work where that might be an issue. Although I do agree it is bad practice to weigh directly on the plate like this. Now you might be wondering why this 1 ounce platinum bar weighs 31.1 grams rather than the traditional weight of 28.35 grams per ounce. I'm not certain of the exact historical origin, but precious metals and stones were traditionally weighed in troy ounces that correspond to 31.1 grams, while common commodities like grain and food were weighed in standard ounces of 28.35 grams. The systems are centuries old and predate modern scientific standardization. And because people with money don't care for the opinions of people with brains, we're kind of stuck with these unusual masses. Although I am seeing more 1 gram, 10 gram, and 100 gram precious metal bars out there, so maybe things are changing. Now I weigh the beaker after it's been meticulously cleaned and dried. As usual, I'm weighing a few times to get a consistent measurement. I need this weight so we can subtract it later and find the mass of our chloroplatinic acid solution. You might be screaming at the screen that there are still a few dirty spots on the beaker and I should keep cleaning. Those spots are acceptable because whatever they are, they survive to 500 Celsius heat and overnight boiling in aqua regia. If they could survive that, they're not going to dissolve in the aqua regia we'll be using later. I think they're just etched parts of the beaker itself. Anyway, now that we've weighed the beaker, it's time for the fun part, dissolving the platinum bar in aqua regia. I'm going to use a non-standard aqua regia mixture starting with 75 milliliters of water and 100 milliliters of laboratory-grade hydrochloric acid at 37% concentration. I put the flask with cooling water on top of the beaker to serve as a reflux condenser. Then I add 10 milliliters of azeotropic 68% nitric acid. Finally, we turn on the heating until it just starts to boil and dial back a little so it simmers. And there it goes, the platinum bar is slowly dissolving. Normally, aqua regia is made using a 3:1 molar ratio of hydrochloric acid to nitric acid, and indeed I've done that before, but this time I'm using a diluted version with a very small amount of nitric acid. This is because platinum is very slow to dissolve, so a lot of nitric acid and hydrochloric acid react away and bubble out as nitrogen oxides and nitrosyl chloride. I'm using a diluted version so there's less nitric acid sitting around being decomposed by the hydrochloric acid. While the dissolution of platinum also slows down, it still makes better use of the nitric acid rather than using fully concentrated nitric acid at once. So I save on nitric acid and also introduce less impurities along with it. The trade-off is that it's slower. Now as the reaction progresses, the nitric acid is depleted, so every 6 to 9 hours I inject another 3 milliliters of nitric acid and continue heating. I keep doing this until the platinum bar is fully dissolved. So what's happening is the nitric acid is oxidizing the platinum metal, and the hydrochloric acid is complexing with the platinum ions to dissolve it and form chloroplatinic acid, also called hexachloroplatinic acid. At least that's what's happening at the platinum. Most of the nitric acid in solution is just reacting with the hydrochloric acid, decomposing into nitrosyl chloride, chlorine gas, and nitrogen oxides. Fortunately, these gases can also help oxidize the platinum, so we can more efficiently use our nitric acid if we keep the concentration low and don't overproduce them and boil them out. Some will still be lost, but more will have a better chance of being utilized. The flask above the acid serves as a reflux condenser to reduce losses of the acid. It also serves as a splash guard to reduce losses of the valuable chloroplatinic acid from bubbling. Anyway, this went on for a couple of days. Near the end, the amount of hydrochloric acid was running low, so I started adding small top-ups of 10 milliliters or so. And there we go, all the platinum is gone. That was about 1,000 American dollars of metal just dissolved. But I have valuable chloroplatinic acid now. At this point, I now need to destroy any lingering traces of nitric acid. I can't have it contaminating the chloroplatinic acid, as it could have unintended effects on future reactions as well as generate gases on storage. Fortunately, I can take advantage of the very decomposition pathway I've been trying to avoid. Already, you can see a faint yellowish haze above the solution. That's nitrogen dioxide generated from the decomposing nitric acid as it reacts with the hydrochloric acid. I keep the heat on and even raise the temperature a little to speed up the reaction. I also add 10 milliliters of hydrochloric acid every 6 hours to help drive the decomposition reaction forward. It does take a while, but I know when I'm done when there's no more haze and it's just clear vapor above the solution. I'm going to add one last injection of hydrochloric acid for good measure and keep heating overnight. Then I let it cool. Now I wash down the flask with deionized water to recover any of the chloroplatinic acid that might have stuck up there, and indeed I saw a yellow color in the wash water. Unfortunately, my camera had an error at that instant and I lost that video. So I'm doing this simulation to show you what I was doing. Normally, I would just redo the reaction, but I'm rather short on $1,000 platinum metal bars, so I hope this simulation is good enough for you. And there is our consolidated chloroplatinic acid. Granted, the washing did dilute a lot of it, but that's easy to remedy. I just turned on the heating again and let it evaporate down to less than 80 milliliters. I was careful not to boil it so it wouldn't spit out chloroplatinic acid droplets. I'm not going to boil it down to dryness because it's easy to heat it too hard and cause it to decompose into insoluble platinum chlorides. So I'm just reducing volume to something more manageable. And there we go. Then I turned off the heating and let it cool. Normally, I would then place the acid in a desiccator and dry it into a solid and then break up the chunks where I could package them into vials. But this time my friends wanted the chloroplatinic acid in ampule form. While vials are useful in that they can be opened and closed at will, ampules are generally more reliable for long-term storage since they are completely sealed. There is almost no chance of contamination or leakage, and well-made ampules have lasted decades, with even some lasting a century. I was also tasked with getting precisely 5 grams worth of platinum metal into each ampule with less than 1% error. So I'm going to leave it as a liquid to make it easier and use gravimetric transfer methods. First, I'm going to check the calibration of my analytical scale. It's been a few days and even the best scales will drift, so I need to check and recalibrate if necessary. I'm keeping the chloroplatinic acid under another beaker to keep the dust out. Anyway, the scale looks good, so we can begin. Now we weigh the beaker with chloroplatinic acid. We already weighed the empty beaker earlier, so by knowing the combined weight, we could subtract the empty weight and know how much chloroplatinic acid we have. I'm weighing multiple times to check for consistency and drift. If they're not consistent or the drift is too great, I'd have to rebalance, repair, or replace my scale. So that looks good. I'm now going to set the chloroplatinic acid aside for 20 minutes. And we're back. Now I reweigh again. I'm doing this to get an idea of the evaporation rate. The scale itself seems to be very stable, so most of the change is not from drift but from evaporation. Looks like the evaporation rate is about 1 milligram per minute. So if I do all the transferring within an hour, I should still come in under the 1% error I'm allowed. With that out of the way, we can start filling the ampules. Let me go get them. And there we are. And here is the ampule we'll be using. It's a 20 milliliter ampule, and I sized it to match the amount of chloroplatinic acid I'll be filling it with. Once it's filled, I'll seal it. First, we need to calculate how much we need to fill it. Let me reweigh the beaker as I'm sure it's evaporated a little. By knowing the current beaker weight, the empty weight, and the mass of our dissolved platinum bar, we can calculate how much solution I need to transfer into each ampule to reach 5 grams of platinum. I know this is a bit unusual, you usually allocate based on the molecular weight of the compound, but I was asked to go by platinum quantity. I'll explain why later. Anyway, we can now start filling the ampules. The process is very simple, we just weigh the ampules first, and then add in the chloroplatinic acid. We keep weighing and adding until we hit our target we calculated earlier. I'm not doing it on the scale for a few reasons. The primary one being I'm old and my hands are no longer steady enough to do it right in the scale. I'm steadier if I hold the ampule in my hand as I'm filling it. The second reason is that chloroplatinic acid is a rather nasty substance and I don't want to accidentally drip it onto the scale and contaminate it. I can clean up my gloves and the glass lab bench a lot easier than the scale. I also don't want to accidentally knock over the ampule and spill it that way. Now most of you probably clicked on this video for the title and are wondering about the value of this chemical. If you go to the Sigma Aldrich website, you can find that 25 grams of chloroplatinic acid hexahydrate is about 2,000 American dollars. I've created about 81 grams worth of chloroplatinic acid here, so let's just round that down to 75 grams and say we have made 6,000 American dollars worth. I spent about $1,000 for the 1 troy ounce of platinum and chemicals like hydrochloric acid and nitric acid, so about $5,000 profit. At this point you're wondering, this sounds like a disgustingly profitable venture, and why is everyone not making this in their basement and undercutting Sigma Aldrich? There are a few important reasons why Sigma is so expensive. First, if you're a large-scale budget buyer who needs very large quantities of chloroplatinic acid, maybe you make industrial catalysts, then you'll simply make it yourself like I am here. So already Sigma doesn't bother trying to sell to large-scale buyers. You can see here there are no 100 gram or 1 kilogram options, only small quantities. Their target market is the small-scale buyers like researchers and testing laboratories. They are not price sensitive, and instead they demand convenience. When their labs cost thousands or even tens of thousands of dollars per day to run, it's more cost effective to buy a few grams of chloroplatinic acid for a several hundred% markup than it is to make it themselves, which has already cost me a few days. Another very big contributor to cost is something less tangible, and that's trust. When you buy from Sigma Aldrich, you're buying trust in that brand. I'm sure a lot of chemists can attest in the comments that they only buy from chemical suppliers they trust and are willing to pay extreme premiums for that trust. So if you want to start making this stuff and selling it, you're going to need to first spend years building a client base that trusts you. Sigma is selling their trust, and that's something most startup chemical suppliers need to earn. The only reason why I'm doing this is because I have built up a tiny network of chemist friends who trust in my ability and integrity to make this compound without cheating them. I'm selling my trust just like Sigma. And I can only really sell to my friends, which is a tiny market. Random chemists on the internet aren't going to buy it from me, just like they won't buy from random basement chemists selling on eBay. The last time I did this was over 10 years ago, and it's unlikely I'll do it again since I don't really have that many friends who would buy from me. So this is not a good business idea unless you're willing to put in the work building a reputation of trust. On a related point, I'm not actually selling this for money. I'm actually trading these for other chemicals I have difficulty getting, as well as future favors and goodwill. Okay, enough about basic economics. Let's get back to the chemistry. Looks like I added too much this one, so I'm getting a long pipette and sucking it back out. I'm using different length pipettes for addition and removal since it's easier to add with a short pipette and easier to withdraw using a long pipette. But using the same pipette for both is cumbersome. Aiming a long pipette is annoying. So you might be wondering why I'm allocating based on platinum weight and not the molecular weight of chloroplatinic acid. In theory, that's not too important as long as you know what you're working with. We can easily interconvert between the two measurements in a 1:1 mole ratio. But I'm allocating based on platinum content because that's the active compound this chloroplatinic acid will be used for. So when doing reactions, it's easier just to allocate based on that. Additionally, chloroplatinic acid molecular weight can be variable. Chloroplatinic acid usually dries as a hexahydrate with water, but the exact quantity of water can vary depending on drying conditions. Additionally, if you heat it too hard, it'll decompose into platinum chlorides, and if you leave it out, it'll actually absorb water from the air since it's very hygroscopic. By using the platinum content, it's easier to mix together different batches of chloroplatinic acid with varying water levels. You're still getting the correct amount of platinum if you're following the calculations correctly. When I label it later, I'll be sure to specify the exact amount of platinum contained in each ampule. Anyway, you might be wondering what these ampules of chloroplatinic acid will ultimately be used for. I'll be honest, I am too. My friends claim they're using them to synthesize various catalysts, but exactly what reaction they're catalyzing and why they need to specify less than 1% air they do not tell me. Maybe they don't want me to blab a trade secret on YouTube or something. Let me know in the comments what reaction or catalyst you think they're doing. I personally have no idea what would require such precision. All the catalyst reactions I know can accept rather large errors of 20% or even 50%. So maybe they're not doing catalysts, But what could need 1% precision but also accept the uncertified quality of a basement chemist rather than a proper analytical standard? My best theory is that there is no precision requirement, and my friends just wanted to watch me waste my time. My friends are pranksters like that. But anyway, it looks like I'm done. I've filled all the large ampules as requested, but I have some chloroplatinic acid left over, so I will produce a series of small ampules containing about 500 milligrams of platinum, or about 1.3 grams of chloroplatinic acid. I could buy 1 milliliter ampules for that, but that's not really worth it for such a small run. So instead, I'm making my own small ampules from pasture pipettes. I'm flame sealing the bottoms, and if my calculations are correct, I'll need about 12 of them. Now I go through a similar procedure of weighing the pipettes first, calculating how much they should weigh after I add the chloroplatinic acid solution, and filling until I get there. At this point, I'd like to say thanks for watching this far. Who knew there would be interest just to watch a chemist at work? So please subscribe if you haven't already. And there we have it, a bunch of chloroplatinic acid ampules containing 500 milligrams of platinum to within 1% error. Now if you look at all of them, there is the tiny issue that filling them was rather messy, and there are drops of the valuable chloroplatinic acid sticking to the lips of the ampules. When we flame seal them later, they'll burn and prevent a clean seal. So in each ampule, I'm going through and very carefully washing them down with a few drops of deionized water. It's a delicate process since I can't spill any of it. We already measured the exact amount of acid and we can't mess that up. The extra water ending up in the ampule isn't a problem as the amount of platinum remains the same. And here they all are, washed and ready. At this point I could seal them and be done with it. But I'm going to take it a step further and dry them inside the ampule. I can't just heat them because they could decompose. And I can't just evaporate them since chloroplatinic acid is hygroscopic. So I'm going to use the mason jar desiccators I showed in a previous video. The idea is that I have a mason jar used for preserving food and I put in a plastic tube of desiccant. In this case I'm using sodium hydroxide since I'm also removing the excess hydrochloric acid. I store the ampules of chloroplatinic acid inside the jars, and given enough time the desiccant will slowly dry the ampules. To help it along, I evacuate the mason jars using this mason jar vacuum sealer attachment and connecting it to my aspirator vacuum pump. By evacuating the jars, the vapor diffuses faster as it doesn't have to push through as much existing air to get to the desiccant. But overall, the process will take weeks. I also have to replace the desiccant every week as it gets used up and saturated with water and hydrogen chloride. At this point I should mention I made a mistake with the earlier setup as I used a full tube of desiccant. This was a bad idea as when I went to replace them a week later there was salt creep coming up the walls of the tube. Here is a tube where salt creep happened. The hydrogen chloride evaporating from the chloroplatinic acid reacted with the sodium hydroxide to produce salt that deposited as these crystals and creeped up the walls. We don't want them accidentally creeping into the chloroplatinic acid, contaminating them. So in later desiccant replacements, I use tubes only half filled with sodium hydroxide. And here we are a few weeks later, and it looks like we've successfully dried the chloroplatinic acid right in the ampules. Before I seal them, if we look closely, there are tiny amounts of acid dried in the upper regions of the stem of the ampules. Because this part will be broken off during use, that small amount will be lost. So to fix that, I'm going to wash down the sides of the ampules one last time and then dry them again. This will ensure perfect recovery of the valuable chloroplatinic acid later. And there we go after desiccating again for a week. Let me get those out. And that looks great. I can't leave them out for too long since they'll start absorbing water from the air, so I'm going to flame seal them all now. You might be wondering why I went through the extreme trouble of drying the chloroplatinic acid. You are right, most of the time ampules are used to store liquids, not solids. I did primarily for stability. Sometimes with a liquid, when you break the ampule, the shock flings out some of the liquid. One time I lost an ampule of expensive deuterated tetrahydrofuran that way. So by drying it into a solid, I reduced the chances of it being lost during breaking. A secondary reason is for safety. If the ampule should accidentally fall over and break, the contents wouldn't spill out and make a toxic mess that's troublesome to clean up. And if it's solid, there is a very good chance it could be completely recovered and transferred to a vial without any contamination. Of course, this begs the question how to actually use one of these if they're dried solid and stuck in the ampule. What you would do is after you snap the glass stem off, you would add the solvent and dissolve it in the ampule itself. Once it's all dissolved, it can then be pipetted out into your target reaction. Interestingly enough, this method of storing chemicals dried to the container is pretty common for extremely tiny quantities. You can buy certain super exotic chemicals in milligram or even microgram quantities. And rather than being sold as a single grain of powder in a vial that can be easily blown out when you open them, they are sold as dried smears in the bottom of the vial or ampule that you have to dissolve out. It's the only way to reliably store and retrieve such extremely small quantities without a bulk carrier solution or solvent. And we are done sealed ampules of chloroplatinic acid. For safety and cleanliness, I'm going to take them all and soak them in a solution of sodium metabisulfite. The reason why I'm doing this is because the chloroplatinic acid is a rather nasty sensitizer. Exposure to it can result in a rather nasty allergic condition called platinosis, even in people that aren't normally prone to allergies. While I was extremely meticulous in my cleanliness procedures, and I didn't have any spills, drips, or accidents that I know of, there might be some residual contamination I didn't notice. So by soaking them in sodium metabisulfite solution, I reduce the chloroplatinic acid into considerably lower toxicity platinum metal particles that are safe to touch. This way I can ensure these ampules are safe to handle before opening even without gloves. And there they are. I love how they all look like they're standing up due to buoyancy effects. I'm going to leave them in there for a day. And here we are the next day. Let me wash off the sodium metabisulfite solution and dry the ampules. And there we go, safe to handle ampules of chloroplatinic acid. At this point we can weigh them, and since the glass ampules are all very similar in weight, we can get a rough idea of the weight of the chloroplatinic acid. For 5 grams of platinum, we know that as in each ampule, the expected mass of chloroplatinic acid hexahydrate containing that is 13.27 grams. And it looks like the measurements are all very close to 13.27 grams. I'm actually surprised the mason jar desiccators were that good at drying the ampules. I was expecting some lingering excess water to remain. So these are ampules of relatively pure, dry, and stoichiometric chloroplatinic acid hexahydrate. And with that, I can make accurate labels for them. Although as said before, the chloroplatinic acid is viciously hygroscopic, so it'll only be accurate while it's unopened. As soon as it's opened, it'll start absorbing humidity, throwing off the weight. I am doing such a horrible job aligning these. Labeling machines are not that expensive, and if I were doing this on a large scale, I might have used those. Okay, that's done. Let's label these small ampules. They're too narrow for a wraparound label, so I label them like a flag. While it is possible to make a very tiny label with small print, I'm old and my eyesight is even worse. Now, something not visible on camera is that these labels are vinyl rather than paper. Vinyl is waterproof and chemical resistant, so I'm hoping these labels will last longer than paper ones. But only time will tell. You might be wondering why all my ampules are bulging slightly at the top. This is just a quirk of how I flame seal my ampules. The flame heats the air in the ampule, causing the air to expand and push the molten glass out in a bulge like this. I let this happen because it tells me the ampule is sealed enough that it has to bulge rather than simply release the air through any hidden holes. An unsealed ampule would not bulge, so I prefer the bulge to indicate to me that the flame seal was successful. Of course, that's what I tell myself. Anyone decently skilled in glass blowing can perfectly seal ampules without bulging. That's like the most basic skill. Okay, that's done. I'm going to trim these down so they're a bit neater. And there we go, now it's looking nice and professional. Although I do apologize to those of you with OCD who are screaming at the screen that the labels aren't perfectly aligned. Finally, I'm going to vacuum seal the ampules into plastic bags. This is optional as the ampule itself is already perfectly sealed. but the airtight plastic bags are a backup in case the ampule breaks during shipping. The chloroplatinic acid will remain dry and solid, and so any chemist that finds it later can still recover it and put it in a vial. Without a plastic bag, the broken ampule will slowly absorb water from the air and leak out everywhere, losing the valuable product as well as making a toxic mess. As you can see, drying the contents and vacuum sealing it are complementary storage techniques. In case you're wondering, I'm just using a regular kitchen vacuum sealer unit meant for preserving food. And these vacuum sealer bags are similarly available domestic ones. There's nothing special or exotic about this if you want to vacuum seal your own stuff. Just designate any vacuum sealer you use for your laboratory only and never reuse it for your actual food. Let me trim these down, and there we go, nicely sealed ampules. It looks so professional. I feel like I just bought a bunch of chemicals, but it's the opposite. I just made a bunch of chemicals for other people to get. Anyway, I'll be shipping them in these padded boxes to try and prevent damage. And for the first time ever, official Nerd Rage branded merch. Although these have already been sold or spoken for. So that's how I turned a $1,000 platinum bar into $6,000 worth of chemicals, packaged and ready for commercial use. As said before, I'm not actually getting money out of these. I'm trading them for other chemicals or future favors and consideration. I sure hope my friends appreciate them. These large ones will go to a professional lab that commissioned me to make them. These small ones will be given as gifts to various YouTube chemists I'm friends with. Thanks for watching. I hope that video was interesting to you. Special thank you to all of my supporters on Patreon for making these science videos possible with their donations and their direction. If you're not currently a patron but would like to support the continued production of science videos like this one, then check out my Patreon page here or in the video description. I really appreciate any and all support.